This video is an introduction to the thermal conductivity experiment. The thermal conductivity experiment consists of a thermal conductivity tester that functions with a hot plate that creates heat. We'll go ahead and open this and show you. You have on the upper side a hot plate. This upper plate is heated by a PID controller that sets the plate to a specific temperature. The bottom plate is cool. So you have the top plate, which is a hot plate, and a bottom plate, which is effectively a cold plate. The cold plate is controlled by a glycol water mixture that is circulated through the plate by a cooler. The cooler sets the temperature of the cold water. When you come into this experiment, it should have been running for a while. And the reason is that the way this experiment works is you have a hot plate providing heat that causes heat to travel through a test sample. So the way this works is you have a test sample. Let's use this sample of foam neoprene, for example. This test sample is placed between two small silicone pads as such. This is closed and snapped closed and tightened, and I'll explain that in a minute. The hot plate provides a heat flux, so heat is traveling from the hot plate to the cold plate through the sample. There are also heat flux sensors on this unit, so it measures heat flux as well as hot plate temperature and cold plate temperature. Again, this should be running, but just to show you how it turns on, there's a switch down here that turns on the cooler. So I'll go ahead and turn that on. This is the main power switch for the data acquisition system as well as the hot plate. This turns on the component that controls the hot plate. And then this is an on button to turn on the cooler to start circulating cool water. Now, this unit here, as you can see, this number is a set point for the temperature that you want the hot plate to be at. Right now you want it to be at 50, but right now it's actually, according to this number, at about 40 degrees Celsius. So when you come into lab, you should see that this unit has been running for a while, and the reason is that it takes a long time for it to reach equilibrium. This unit will allow you to measure thickness as well as heat flux in terms of millivolts and hot plate and cold plate temperature. In order to get hot plate temperature, this switch needs to be turned down. Right now you have hot plate temperature. If you turn the switch up, it'll give you cold plate temperature. This display here gives you the voltage reading from the heat flux sensor. And as far as how to measure the thickness of a sample, it can be a little, well, it's not complicated, it just takes a little bit. So what you end up doing is you take out the sample, right, just leave the silicone pads in there, close the unit, close the hatch or the latches, and then turn this knob in order to tighten it. Now, take note, it's opposite to what's intuitive. Turned to the right, it loosens. Turned to the left, it tightens. So I'm going to go ahead and tighten it. Now, when do you stop turning? You'll see here that there is a green light. You are to keep turning the knob until that green light goes off. So I'm going to go ahead and keep turning it until that green light turns off. But you have to be careful when it starts to become, when you start turning the knob and it starts becoming a little tough to turn, lighten up a little bit because you need to stop. There it goes off. I'm going to loosen it again until it turns on. There you go. when it starts tightening up, the light goes off real quick, and you want to be able to release the handle as soon as the light goes off. So I'm turning the handle slowly right now, and then the light just went off. Once that happens, you come up, take a dial reading. This dial reading would correspond to 78, which would be the left side of the decimal place for the black needle. And then the right side of the decimal place is the red needle. So this would be 78.54 approximately. So take note of that. Loosen it up as much as possible. Well, not as much as possible, but loosen it up significantly. You should see the light come back on. Open it up, loosen the latches, open up the unit, take the sample that you're going to test, put the sample, whoops, that almost fell, put the sample in the unit with the one silicone pad on the bottom and the other silicone pad on the top. Close the latches. And then turn and tighten the unit, or tighten the turn the knob to tighten the plates together until the light turns off again. And then come back up, take the reading from the dial again. This looks like it's about 83.3 or 28, so 83.28. You would take that final reading, subtract the initial reading, and then multiply it by 2.5. Basically, it's saying that for every turn of this knob, it raises or lowers the plate by 2.5 millimeters. I believe it's 2.5 millimeters. And that'll give you the thickness of the sample. So that is how the unit operates. The overall purpose for this experiment is for you to find what the thermal conductivity of a silicone sample is. This sample is silicone. This sample has a thermal conductivity that is too high for this unit to accurately measure. Actually, this unit has what's called a minimum resistance that it measures accurately. So what that means is that your sample has to have a minimum thermal resistance in order for this unit to measure its thermal conductivity. Resistance is thickness divided by thermal conductivity. If the sample doesn't meet that minimum resistance, which this sample does not, it, in a sense, overwhelms the heat flux sensors. You don't really get a reading because it's out of range of what this unit can measure. So what you do is that you can pile this sample on top of another insulation sample or another sample that does match the thermal resistance. So I'm going to go ahead and loosen this again until the light turns on, and then give it a few more twists. I'm going to open it up, and I'm going to take out the sample that's in here. Okay, so this sample is foam neoprene. This matches the minimum thermal resistance. When you come into lab, this sample will have been in a testing unit for a significant amount of time. So the unit reached equilibrium. I'll explain how you know it reaches equilibrium in a minute. You measure the thermal resistance of this sample, and then what you end up doing is that you put this sample in the unit with a silicone on top of it, right? Put it inside as I just explained, and then take the thermal resistance of both of these samples combined. Now, what that will do is that it will give you an effective thermal resistance of one on top of the other, and then you can use thermal circuits to extract the thermal resistance of the silicone sample, knowing what the thermal resistance and thermal conductivity is of the foam neoprene sample. As far as when you hit equilibrium, what you're going to do is once you put these samples in, you are going to wait a half an hour, 45 minutes possibly, and then you are going to start taking heat flux sensor readings. So what you're going to do is take this heat flux sensor reading, the voltage from the heat flux sensor, and you are going to take that measurement every 2 minutes. Once the reading from the heat flux sensor changes less than 1% or 2% within 2 minutes, you probably have reached what's called an initial equilibrium. Okay, I hope that's helpful. This concludes the instructional video for the thermal conductivity experiment.